right, let me turn on my, so I don't have my, hopefully I don't have to write. I'll use my calculator. Okay, so series and parallel circuits. Week 2, okay? Lexi, you're going to start week 2, right? Because you're done with week 1. Karen?
I'm not done with that first quiz.
Okay. If you want help, let me know. Okay. So, here we go. These are the circuits that we have. And one of these is series and one of these is parallel. So, when it says something about series, that means that the light bulbs or the resistors or whatever you're using are all one right after another. They're all in series, okay? When it talks about a parallel connection, that means that they look kind of like a ladder, or they're one right after another, okay? I guess, I don't know if you can think about parallel lines in math. You know, parallel lines are one right after another. Okay, so that's what we're doing, series and parallel. And circuits can be either one. Circuits in your house are parallel circuits, all right? Because if the reason that they have them as parallel circuits is because if one light bulb goes out, not all of the lights in your house will go out. In a series, if one of these go out, that means that the connection is not, it's not a closed connection anymore, so it goes, all of the lights go out. Does that make sense?
Yeah.
Okay. So in a series circuit, the current can only take one path, right? There aren't those multiple places. It can only go one way. It can only go around the circuit. And the current is going to flow through every part of the circuit. So it's going to be the same current that's going through every part. So one of the things whenever you get into week 2, that's one thing to remember. In a series, the current is always the same, all right, in a series circuit. Okay, so when one bulb is removed from this circuit, then all of these are going to go out because it's like the connection has been broken. Like in the first, I think the first assignment that you had, they talked about a closed circuit. If this right here makes this circuit open because it goes up here to this first one and it stops because it says, okay, there's no connection there. I can't go any further. All right, so none of these 2 lights that are left here are going to get any current. Okay. So if you add a resistor, like another light, lights are considered resistor, then the total resistance in this circuit is going to go up, right? Because the resistance total is R1 plus R2 plus R3 plus R4, so the total resistance is going to go up. All right. So current in a circuit will go down. Why do you think the current is going to go down? Again, it's the same current that goes throughout. However, if you add another resistor, why is the current going to go down?
Because it's going to need more energy to work with the rest of the...
Exactly. I know what you're trying to say, and that's exactly correct. Because as it goes through, the total resistance is going to go up, and the resistance is just it stops the current, right? It makes it so there's not as much current or not as much energy. Good. And again, if you remove a light bulb or one of them go out, they all go out. So let's think about your Christmas tree lights. Do you guys have any that when one bulb goes out, the whole thing goes out?
Yes.
So those are wired in a series. Where have you been?
Getting ready to leave?
Okay, well, we're in a webinar, sir.
Well, I'm in your class, so technically I can be in here.
That's true. Okay. But if you have those Christmas tree lights and one of them comes out, or you can take one out to replace it, like if you want it to be all white but you have one blue in there or something, you can take that out and you'll still have the white ones going because that means that they're wired in parallel, okay? So current is the same at all the points in a series, and that would be something to really, really remember. Ohm's law is the way that you find the current using total resistance and total voltage. Okay, so we're going to look at this, and I want you guys to do this. We're going to calculate the current in this example. So go.
So what do we do?
Calculate the current.
Oh, that's what it says.
And I'm going to draw this picture. I don't know how well. I'm not, since I don't have my. Karen, you're calculating, right? Okay, so I don't know if you saw this. I don't know if you've done, again, the second. But Ohm's law is V is equal to IR. Okay, so that's Ohm's law, and that's what we want to use here. All right, so if you use this right here, this triangle, and we want to calculate the current is I. Focus.
Yes, I'm focusing, sorry.
The current is I. You cover up that I, and then what you have is voltage divided by resistance. Okay? So, what is our voltage in this case?
60.
Okay. What is our total resistance? 30. So it's 60 divided by 30. So what's my current here? There we go. 60 divided by 30. 2 amps. Okay, current is amps.
I actually just guessed that, so I'm surprised I got that right.
Really? Look, let's cancel out the zeros. What's 6 divided by 3?
2.
Ah, there you go. It's easier than you thought, isn't it? Okay, so in a series, it really is. It is pretty easy. Excuse me. So voltage in a series, it is reduced every time you go around for each resistor that you cross. Okay, does that make sense? Every time you go across a resistor, it's called a voltage drop. All right? So now what we're going to do is we're going to calculate the voltage. This is the same problem. And again, remember our lovely triangle. And if we want to do the voltage, we're going to cover up the V, and we're going to multiply I times R. Okay? This triangle, seriously, is something that you should put into your notes, because when it comes time to do the final, or whatever, the midterm, whatever you want to call it, you're gonna need to know this formula, right? And it's V is equal to IR. All right, so we want to calculate the voltage, and what we want to do is the voltage drop across each resistor. All right, so we know the amps because we just calculated it. What was it?
22.
2.
Isn't that 20?
No. Here, let's look.
Oh, wait, no, I'm thinking the other
You're
thing.
thinking, okay, she's maybe thinking 60 divided by 3. Okay. All right, so remember that our voltage, or I'm sorry, our current was 2 amps. So we know our current, we know our voltage because our voltage is right there. So what is the voltage drop across this 6 ohm resistor? So we want to find voltage, right? So you cover up the voltage, and we're going to times the current, which is 2. So 2 times 6 is what?
Wait, what? 2 times 6.
2 times 6. I'm sorry, did you say 12?
Yeah.
Yeah, it's 12. Hi, Austin. So, I don't know, can you see that 12? Sort of. All right, so it's 12 there. What's going to happen is the resistance across each one of these the voltage across each one of these resistors should add up to 60. Okay? So what is our voltage then across this second one? Change my color. So we know that our current is 2. We know that our resistance is 14. So what? 28. The other one will be 20. Kind of, you can see that. And this one is going to be 20. So what's 20 plus 12 plus 28?
12 plus 12 plus 28.
12 plus 28 plus 20. Okay. Let's see. 12 plus 28 plus 20, right? 60. And it's got to add up to 60 because that's how many volts that we have there. Make sense? Okay. So that's a series circuit. I don't know if we have one more here. Okay, total resistance. Remember, again, you're going to add up all the resistance. We added up all the voltage drops. We're going to add up all the resistors to get the total resistance. So we kind of already have done this. So 5, 3, and 2. What is our total resistance?
The total resistance.
Mm-hmm. In a series circuit, you just add up. Okay, that's right. So what is our total resistance, Austin? We're going to add up all the resistors. Yes, it's 10. 5 plus 3 plus 2, it's 10. In a series circuit, all you have to do is add up those resistors, okay? Series circuit is going to be easy. Okay, so this one, if you're here, you don't have to worry about doing this. This sample problem is going to be our, what is that called? That question, discussion question for the webinar, okay? So I guess I need to, okay, that's good. That's our discussion. And you need to answer all 3 of those, okay? So it's not really difficult because we just went through all of that. So you should be able to do this pretty easily. All right, now we're going to talk about parallel circuits. And this is a little bit more difficult, all right? So a parallel circuit has at least one point where the current divides. And there's more than one path that a current can flow through. And the paths are known as branches. All right, so lights in a parallel circuit, if one of them goes out, then there's still a place for the current to go, right? It can still go here. It can still, go here. The only thing is it can't go up here in a parallel circuit. Does that make sense? So if this light bulb goes out, these 3 can still light up. All right. So in this case, if you add up all the resistors, the resistance, if you add a resistor in a parallel circuit, the resistance goes down. And there's a reason for that. There's a way that you're going to add up the resistors that's different than in a parallel. And it's a little more difficult, but there's an easy way to do it too. And the total current will go up if you add another path because it's got another place to go. Does that make sense? Yes?
Yes.
No? Okay, thank you. Excuse me. So if you remove a light bulb and one burns out, the other ones stay on because you still have a closed circuit. Just where that one light bulb is, that's an open circuit, so no current can go through. All right, so the current that flows into each branch, the same total current must flow out again. So if 3 amps flows in, 3 amps has to flow out. Make sense? Okay, and current depends, again, it depends on the resistors in each branch. So, now, All right, we're going to calculate the current in these in this circuit. Okay, so again, remember your triangle. We want to do the current. So what am I going to do? Let's calculate the current. Let's do this. We'll calculate the current that's going to go through here. Not the total current, but the current through that first branch.
36.
It's 24, right? Remember,
24 and 12.
V equals IR. Current is the I, right? So the total resistance in that first one is just 12. So it's 24 divided by 12. So how many amps are going through this first part?
12?
24 divided by 12.
Oh.
What's 24 divided by 12? 2. 2 amps here. All right? So of our current, 2 of the amps have gone through here. What about over here? How many amps are going to go through here?
Isn't it 2, 2?
Nope. Because this is a parallel circuit. So what goes on is that your current is going up, and okay, part of it's going to go this way, but then part of it's going to go this way. So we already had 2 amps that went this way, so there's still something going this way. Again, look at this formula. V is equal to IR. V is 24. Resistance is 24. What's your current? It's 24 divided by 24.
Oh. Okay. 1.
1. All right. So we got 1 amp here, 2 amps here. So what's the total amperage, or what's the total current?
I just remembered. I didn't go to you yesterday.
What's the total current? What's 2 plus 1?
3.
Yes.
Are you leaving? Okay, good.
Okay. So we're going to talk about voltage, and this one is pretty easy. What's voltage in a parallel circuit? It's the same across each branch because each branch is on the same wire. All right? So this one's pretty easy. What's the voltage in this circuit?
24.
Yes, it's 24 across each branch.
No, thank you.
Excellent. Easy, right? Now the resistance. This is a little bit different, and this is something that you need to write down in your notes, and if you don't, I'm not helping you, because that makes me sad. Okay, so resistance in parallel. To calculate the resistance, you calculate the current in each branch, and based on the resistance, and we're going to use Ohm's law. But this is where you can do something that's a little bit different, but it's a lot easier to calculate the total resistance here. So if you have something in parallel, what you're going to do is you're going to take the product of both of them. What does product mean?
The answer.
It does mean the answer, but what does it mean that you do when you say the product of these two numbers is? What did you do to those two numbers?
Divided.
Nope.
Times.
Times, exactly. So if we want to get the total resistance and we only have 2 parallel parts, we're going to multiply 12 times 24. All right, what's 12 times 24? Come on, let's do it in your heads. Yeah, I know. I couldn't do it in my head. Ready?
288.
288. All right, somebody did it in their head.
No.
Okay.
Calculator.
288. And then, okay, what's 12 plus 24?
Hold on. 26. I mean 36.
And I'm trying to make eights here.
No, wasn't it like 38? That was
6, it's 36. Is that what you said?
Oh.
Yeah, 36. Okay, so what's 288 divided by 36?
Wait, what's what?
288 divided by 36.
Wait, what?
288
Oh.
divided by 8. So the total resistance in this circuit is 88. Okay?
Okay.
Does that make sense?
Yes.
If I were to add, just real quick so that you know, if I were to add another resistor on here, I would take this 8 and then multiply it by whatever this resistance is. Say if I want it to be 4. Okay? And I would do the same, product divided by sum, but I just do them 2 at a time. Make sense? Okay. There is a harder way. Do you want to know the harder way?
Yeah.
The harder way is, I don't know if I can I erase? I don't think I can erase. Okay, so the harder way is 1 over 12 plus 1 over 24 is equal to 1 over the total resistance. Okay? So it's just a little harder. All right. So practice problem number 2. We're going to draw a parallel circuit with 2 resistors, 1 in each branch, and a 12-volt battery. So what is the voltage across each resistor? In a parallel circuit, voltage is always,
The first thing.
so what is it? If we look at the problem, what is the voltage across each one of these resistors?
Voltage is divided.
In a parallel, things that are parallel, the voltage is the same across each resistor. So if you start out with 12 volts, it's 12 volts, it's 12 volts. It's 12 volts across each resistor.
So when we multiply?
Well, you wouldn't have to multiply this one. You just know because it's given to you there, okay? But that's good. Yeah, if you wanted to find it, you would do that. Voltage is equal to IR. All right, next one. What is the current flowing through each branch? We don't know the resistor, but it's 12 divided by R. Make sense?
Yes.
Whatever that R is. All right, so this is kind of, this is just to kind of help you. In a series, let me just go. Okay. When we have a parallel circuit, all right, that means that more things can flow through. Does that make sense?
Yes.
In a series, this is where things kind of get all backed up. So if something goes wrong, if you have a crash right here, I probably can't see my little, if you have a crash right here, everything is going to be backed up, right? So a crash here is going to stop everything. So think of that as your series circuit. Right here, crash, nothing's going through. All right? So if I have 3 resistors in a row and I have a crash, then I'm really not going to get anything to go through. However, if I have a crash here and this is in parallel, I have a crash here, all these people can go around, right?
Yeah.
So things can still flow. Does that make sense?
Yeah.
So that's the difference between parallel and series. Okay, that's my toll booth. Adding more keeps the resistance, you increase the resistance, but you still have a current, okay? Batteries, if they are, excuse me, batteries in parallel means that you have less voltage than you would if they were in series, okay? In parallel, that means negative to negative and positive to positive. In series means negative to positive, negative to positive. Okay. One more final thing. There are 2 types of currents, and we talked about this at the beginning. One is a DC current, which is what we are really going to, that's all that we're going to focus on is a direct current. And then the other one is an AC current, and that's an alternating current, and that's what's in your house. Okay? Alrighty. Questions, anybody? Thank you, Austin, for coming. Thank you for participating. Remember, you guys, you go in and just say that you attended, and you'll be good. All right. Austin, any questions? If he's still here. Oh, he is, yes. Okay. Remember, just type in attended and you're good to go. Have a great day. All right.
Are we done?
I know you're sad about it, but yes.